Welcome to this explainer. Today, we're unpacking the absolutely vital process of taking messy, raw data and engineering it into the perfect numerical diet for machine learning models. If you've ever wondered why a highly sophisticated model just completely fails despite seemingly good data, well, the answer almost always lies right here, in exactly how that data was prepared.
Here's our roadmap for today's data lifecycle journey. 1. The feature vector reality. 2. Inspect and scrub. 3. Scaling and normalization. 4. Binning and bucketing. 5. Synthetic polynomial features. And 6. The perfect feature.
All right, let's jump right into Section 1, the feature vector reality, shattering the raw data illusion.
Let's confront a massive misconception right out of the gate, shall we? We so often think a model just grabs a row of text, numbers, and strings straight from a database, kind of like a human reading a spreadsheet left to right. But do machine learning models actually eat raw dataset rows directly? The surprising answer is no, they absolutely do not. No way.
Instead of raw data, models only ingest what we call feature vectors. These are super clean floating point arrays that represent processed values. This means feature engineering isn't just some optional best practice, it's a critical translation step. You literally have to convert non-numerical strings and mixed formats into pure math. If you skip this translation or, do a sloppy job of it, your model is essentially flying blind.
Moving right along to Section 2, Inspect and Scrub, removing the bad apples. Before we can mathematically transform anything at all, we have to inspect our raw ingredients. Think of your dataset like a massive apple orchard. You really have to meticulously scrub your data because even a few wormy, bad apples can spoil an entire large dataset. Basically, feed your model healthy data and it thrives. Feed it junk and its predictions become totally worthless.
As engineers, we spend an enormous amount of time hunting for these bad apples. You can actually use scripts to automatically flag problems, like omitted values, or say a thermometer reading 1,000 degrees, which is obviously a glitch, or a server log in the exact same event twice. Once they're flagged, you fix these by either deleting the corrupted examples entirely or correcting the bad labels.
And that brings us to outliers, values that are drastically different from the rest of your data. You really have to investigate these carefully. Sometimes, they're just typos that need to be deleted. But sometimes, they are perfectly legitimate, rare data points that your model actually needs to understand. If an outlier reflects reality, keeping it might just be the secret sauce to helping your model make accurate predictions in extreme scenarios.
Okay, Section 3, scaling and normalization, leveling the playing field. So once our data is clean, we have to prevent our model from getting confused by wildly different numerical scales, like comparing an age of 25 to an income of 80,000. That's going to throw things off. This toolbox summarizes exactly how we scale data down to a level playing field, like a nice, neat range of 0 to 1. Doing this stops the model's learning algorithm from wildly overcorrecting. It also prevents mathematical overloads, often called the NaN trap, which happens when formulas try to process massive unscaled numbers.
What's truly fascinating here is that because most real-world data isn't perfectly flat or uniform, z-score scaling is often a much better choice than basic linear scaling. Nature absolutely loves bell curves. Z-score scaling maps values based on standard deviations from the mean, which is just perfect for normally distributed data, like human heights or test scores.
But hey, what if your data looks like book sales or movie ratings, where a tiny fraction of blockbusters accounts for massive numbers, creating a heavy tail? In that case, you desperately need log scaling. Without it, a linear model thinks a book that sells 1 million copies is literally 10,000 times better than one selling 100. Log scaling brilliantly shrinks that massive gap down to a manageable, logical ratio for the model to process.
Let's move to Section 4, binning and bucketing, handling clumpy data.
Sometimes the relationship between a feature and a label isn't a straight line at all. It's, clumpy. Think about retail foot traffic. People shop the most when the weather outside is comfortable, right? Not when it's freezing or boiling. By binning, which is turning a continuous temperature reading into distinct categorical buckets, we literally force the model to learn separate, distinct weights for each specific temperature clump.
But here is an absolutely crucial warning. You must avoid creating too many bins. If you make a unique bucket for every single fractional temperature reading, you're going to end up with empty bins. And if a bucket only has, say, 0 or 2 examples inside it, the model simply cannot learn a reliable statistical weight for it. It absolutely needs volume to learn.
So if your data is highly skewed, quantile bucketing is your absolute best friend. Instead of making all bins the exact same numerical width, quantile bucketing intelligently adjusts the boundaries so that exactly the same number of data points fall into each bucket. This effectively hides those wild outliers and gives equal information space to the bulk of your actual data.
Section 5. Synthetic polynomial features. Learning in curves.
Okay, so what do we do when our dataset classes are fundamentally mixed together in a way a straight line just can't separate? Imagine a scatter plot where one category forms a dense circle right in the middle, and the second category forms a wide ring around it. When a straight line fails, we can actually use a curve to cleanly separate the data, and we can do it without abandoning the efficiency of our linear models.
We do this through a polynomial transform. Essentially, we are actively creating brand new synthetic features literally out of thin air. By multiplying a feature by itself to add a hidden squared term, we give the model a synthetic feature that mimics physical world relationships, like gravity. The model just sees this squared term as a normal feature to weigh, but the geometric result is a beautifully curved boundary that separates what was previously impossible.
And finally, Section 6. The perfect feature, the final checklist.
We have made it to the end of our data lifecycle journey. The final product, the perfect feature, is meticulously scrubbed. It's clearly named so human engineers can actually understand it. And crucially, it uses sensible Boolean flags to indicate missing measurements. Never, ever use a fake magic number like, I don't know, -999 just to mean data missing. Always create a separate feature flag instead.
I want to leave you all with a bit of a provocative thought. Take a hard look at your own data pipelines today, because your model's predictions will only ever be as good as the features you engineer for it. What hidden junk is lurking in your raw datasets right now? Check your outliers, graph your distributions, and remember that engineering data is an art just as much as it is a science. Thanks for joining me on this explainer. Catch you next time.